Welcome, everybody. I think we're beginning to stabilize in terms of numbers, and I make it 8 o'clock. This is the first of the October classes as we head closer to round one, which happens in November. So as with previous weeks, it's highly advisable that you get some paper and a pen and be ready to take notes and do some thinking. Physics is a very active process, so we don't want you just to be entertained, although I know Dr. French is always entertaining. Physics is active, so we want you to actually take notes and actually do some physics. Take it away, Dr. French.
Okay, good evening, everybody. Welcome to BPhO Round 1 training. If you're new, a massive welcome to all of you. So this is our fourth session. If you want to have a look at some of the questions that we're going to be looking at this evening, they're all from the 2022 BPhO Round 1 paper, as the previous ones have been. And we're going to look at F, I, Q, and T. So we're going to have a look at, start with some mechanics. We're going to have a look at some optics today, which we haven't really touched on before. Right, so let's make a start. So as Professor Chung mentioned, it would be really good if you could sort of follow this on paper. And if you are new to this, there are some questions which are sort of one question per page, which can look a bit like the ones I'm going to be working through. So if you're not sure how to access that, we'll put some information in the link, and you perhaps print those out for next time. But in the meantime, sort of enjoy. So let's go and find out where we were. So we're going to start with F. So I'm just going to scroll down and we'll find that. Okay, here we go. Right, so we're going to start with some mechanics, an inclined plane. So let's just have a look what this is all about. So a body is projected with velocity v up a plane inclined at an angle alpha to the horizontal. And intriguingly, when it returns through its starting point, it's now moving with half the speed with which it was projected. All right, so this is about a body sliding up a plane. So first thing we're going to do is put that into a picture. So let's go and draw something. So there we go. So let's have our inclined plane looking a bit like this. Okay, and I always exaggerate the angles of my inclined planes, because there's going to be forces involved, so we want plenty of space. So there we go. Here's our little body here of mass m. So let's put the forces onto this. So I can have it as well, because this is dynamics, right? So we're probably going to be involving Newton's laws, although actually the first thing we might want to consider, almost any mechanics problem, if we can get away with it, in fact, any physics problem, is conservation of energy. But energy involving work done, there's something involving friction. So a good start is to draw the forces. So let's draw it. So we've got weight mg. We've got our gravitational field acting like this. We've got an inclined plane. So let's just put the forces on first. So we've got friction, which is opposing our motion initially. Let's call that force friction F. And we're reminded by Newton's law, I think it's Newton's law of friction, that it's proportional to the normal contact force. All right. So really, the contact force of the body on a surface is really a sort of a more general angle, but it makes sense to decompose it into a friction which is acting along the plane and a normal contact force which is acting perpendicular to it. So for those of you in the upper sixth, you'll be very familiar with this. Those in the lower sixth, you might be meeting this, and this might be new if you are not in those categories. However, if you've been on the climbing wall, I've just been supervising a climbing wall. This is exactly how we are able to climb with shoes on the climbing wall and smear by increasing the normal contact force, which then increases our friction, which might be opposing gravity if we're climbing. So let's draw a normal contact force. I'm going to call that R, actually. I don't really like using N for, I'm going to scrub that out because N kind of is very close to Newton's. So I'm going to call that R. I was going to relabel that. I hope BPhO don't mind. And there we go. So that's a normal to the surface. We can draw a right angle there. And it's going to make sense if we're talking about forces to have a reference frame. So we're going to have a frame of reference, and it kind of makes sense to have X being going up the slope and Y being perpendicular to the slope. We need a coordinate system, otherwise, although these are vector quantities, coordinate independent, to make sense of what's going on, we might want to talk about, a distance and a speed, in a direction. So we need a coordinate system. Right, so we've got an initial velocity. Let's change color for that one. Let's go for purple. All right, so my initial velocity is going to be V. All right, and this is the thing which, if we half it when it comes back. So here we go. Our sort of body moves up to this point here. And let's have that distance to be X. All right, that's that slope. All right, let's have that distance there. That's going to be handy. All right, so it's going to go up the slope, stop, and then slide back again. And the idea is that the speed is half of what it was before because it's doing some work against the frictional force. All right, so angle alpha to the horizontal. So that's another thing to be careful of. That's going to be like so. And do we have anything else? I think, oh, well, we could do some geometry first. So if you think the angle I've got here, that's going to be 90 minus alpha. So alpha is also going to be this angle here. And those angles allow us to resolve the forces in the x and the y direction. A nice thing about the friction force and the normal contact force, they're aligned with the axes, but the weight we can kind of decompose into x and y components. So let's do that first, actually, because that'd be quite useful. Let's resolve the forces in this situation because we've got some dynamics in the x and y. So let's go and do that. So actually, the y direction, there is no acceleration because this particle is sliding up and down the slope. So let's do that first. So let's go for Newton's second law. Mass times acceleration is vector sum of force. And we're going to do that parallel to the y direction because that's going to be in equilibrium. So our mass times acceleration in this direction is going to be 0, all right, because it's not popping off the slope, as it were. It's just sliding along the slope. So we can just remind ourselves that's going to go on. So it's going to be sliding up and down the slope. All right. And again, all these things, if you're doing this quickly as part of BPhO Round 1, will be kind of buzzing around in your mind. But perhaps if you're training for this and you're doing it in slow time, writing those thoughts down is kind of really helpful. And the more you do it, and then you kind of don't need to write them down if you're going to do it at speed. Okay, so our mass times acceleration in the y direction is going to be r, because that's the normal contact force. And we're going to kind of decompose our weight. So for those of you who are experienced with this, you'll know that's mg cos alpha. But for those who are not, let's just do that below. So we can always think about our vector, which is our weight, and we can break that as a vector sum of two other things. So that's my angle alpha. What I can do is I can say, okay, well, it's a vector sum of a green vector, which is, so if mg is the length of my weight here, so mg cos alpha. Remember, in trigonometry, it's very good to think about these as multipliers. So what do we multiply the hypotenuse by to get the adjacent side? That's cos alpha. So mg, so I'll do that in green, so that's nice and consistent. So mg cos alpha, all right, in the sort of y direction. And in the other direction, let's go for blue for this one. We can think of my weight being a vector sum of mg sine alpha in that direction here. All right, so the red is the green plus the blue, because vectors add tip to tail. So this is, we resolve the forces. So in this direction here, this is our vector sum of force. And it's a really good tip for mechanics problems. If we're doing Newton 2, try not to simplify too soon. So I always think, right, mass times acceleration is vector sum of force. Let's do that. And let's not try and simplify it. Just make sure I've got all the terms in the right sign, that the vectors go in the right direction. Then I can do some mathematics and simplify it. So my next stage is, well, therefore, my normal contact force is equal to mg cos alpha, all right? And we're told that our friction force, therefore, F is mu r. I've not used it mu n, so mu r, which is therefore equal to mu mg cos alpha, all right? So that's going to be our friction force. Now, we could start to go and do some dynamics with this one. We could work out the acceleration going up and all of that. That will be absolutely fine. But I think it's always good to start off with energy as a sort of first port of call, because that's kind of, it doesn't depend on direction really. It's a scalar quantity. So I think we're going to do it this way. So if you fancy doing another way with just using Newton 2 in the x direction and sort of using constant acceleration motion, that'd be absolutely fine. But we're going to do it with energy. So let's go up the slope first. And why might we want to decompose this? Well, because the friction force will change direction when it's sliding down the slope. So let's go up the slope first, okay? So what we're going to do, we're going to do our energy balance. Let's check. Can I confirm, am I coming across all right, guys?
Yep, you're still very clear.
Excellent, excellent. So our energy balance, we're going to start off with a half mv squared, our kinetic energy, all right, initial kinetic energy, all right. And as it goes up the slope, we're going to gain some gravitational potential energy. We're going to do work against gravity, but we're also going to do work against friction. So the work that we do against gravity is mgh. Now h in this case, let's put that there. That will be h here. That's the little height. So mg, and the height is going to be x sine alpha. All right. Again, it's always a good idea to label what we've got, and that's the GPE gain. Okay, so there's our GPE gain, and we're also going to do some work against our friction force because that's in that direction. So force times distance in direction of force is the work done. And we don't have to do any integrals because the friction force is a constant. All right, note constant. Excellent. So Fx, there we go. So that's the work done against friction. There we go. Right, fantastic. So there's conservation of energy. I'm just going to make that a V rather than some sort of little squiggle. Right, and I'm going to put that in a box because that's rather important. So that's quite interesting. So that will tell me what X is in terms of friction and all those other things. So I can substitute for F in this one. So let's go and rearrange this and make X the subject. Remember that what we're trying to work out. So what are we trying to work out? We're trying to sort of work out the coefficient of friction in terms of the angle of the plane. That's the goal. All right. So we need to kind of cancel the velocity. We don't know what that is. All right. So it's going to be some sort of ratio thing. So, okay. So we've got a sensible equation. We must know what X is. All right. So let's go and rearrange that. Okay. Because, you know, that would be useful in terms of it's going to slide X the other way. So it'd be kind of helpful to work out what that is. So let's just factor out X on the other side. So we've got a half mv squared. All right, and we're going to divide that by, if I factorize everything out, so mg sine alpha, and then I've got plus f, and f is mu mg cos alpha. And that is going to be x. All right, so I factored out x from this expression and divided what that goes, that's multiplied by. Now, you'll notice that the mass now cancels. Hooray, right, because we're not told what that is. Fantastic. And there we are. So we've got, let's just simplify this. So x is going to be a half v squared. And maybe what we can do is we can divide everything by g as well. So v squared on 2g. And then downstairs, we've got sine alpha plus mu cos alpha. All right. Okay. Right. Well, that looks like that's going to be useful. So what we now need to do is look at what happens when we go down the slope. And then we can do another energy balance. And hopefully we'll have some sort of similar expression, and then we can do some mathematics. So you notice I'm kind of being kind of positive. I don't know what the answer is going to be, but I've got some idea of the kind of mathematical equations that I need to make that happen. All right, I've got a goal, which is how does the coefficient of friction mu, which appears here, varies with alpha. So I need to get rid of x and v. Okay, that's what I really need. So let's do another energy balance and let's see what happens. So going down the slope. Okay, now all I need to do is another picture. Otherwise, so let's define this. So here we go. Let's just draw that all again. So here's where I start off. Let's have my purple object. And it ends up down here. We've got the same forces, all right, but now friction is acting this way. It opposes the motion. We've got a velocity at the bottom. Let's just call that V dash, shall we? Because it'd be nice to solve it generally, but we know that V dash is equal to V over 2. That's what the question tells us. But it might be nice to actually sort of do it more generally, perhaps. So there we go. There's the weight. There's the normal contact force. That hasn't changed. And there we go. Let's have that angle there. That's alpha, and that's alpha. So what we got? We've got the kinetic energy gain. So half mv dash squared. That's the KE gain. All right, that distance is x as that we had before, all right, because it's, you know, starts going down from the point where it's had an instantaneous rest. So what do? Well, we use mg x sine alpha. All right, that's the GPE loss, exactly what we had before. All right, and what we've got now, the work done against friction. All right, so basically we get the kinetic energy gain is the GPE we lose minus the work done, so Fx. So if you look at what we had before, it looks kind of similar, but the sign of the sort of work done is different. All right. Okay. So we're sort of, the energy balance is we start off with our initial kinetic energy, and that's equal to the work done and the GPE gain. Whereas the energy we gain going down the slope is GP loss minus the penalty that we pay because of friction. All right. So that's the frictional loss. All right. Notice it's quite useful just to kind of talk your way through that. And that's how we get the signs right. This is much more than just plugging stuff into equations here. This is sort of because we're generating them. And this is the harder bit of physics. The solving it, the maths is not too bad, as long as you're sort of trained with it. But it's writing down these equations in the first place is the really key thing. Okay, so that's why we want to take some time over that. Right, so let's sort of pull that all together. And there we go. So what I suggest we do is we can sort of work out. Now, if you think about this one, it'd be nice to have a similar expression that we had before. All right. So let's go and write that down in terms of sort of x. So what do we got? We've got the m's cancel. All right. Well, actually, let's just express that first before that. So let's not get ahead of ourselves. Right. So what do we got? We've got a half mv dash squared equals mg x sine alpha minus, and F is our friction force, mu mg cos alpha. So mu mg cos alpha. And we got an x as well from there. So if we factor that out again, so we've got a half mv dash squared divided by mg sine alpha, okay, minus mu mg cos alpha. All right, so it's just what we had before. And if we divide by we can cancel our m. There you go. All right, so what have we got? That's equal to x. So we'll have something very similar to the box we had before, except now the sign of the mu g cos alpha bit is different. So what do we got? Therefore, our x quantity is going to be v dash squared on 2g divided by sine alpha minus mu cos alpha. All right. So there we go. So if I'm going to sort of put those two things in boxes, we've basically repeated the same calculation, but now our friction term has got a different sign. So what we can do is we can divide one by the other, or set them equal to each other. That's probably the best way of doing it. So if we set 1 equal to, so I want to draw a little sort of line here. Okay, so 1 equals 2, which is x. All right, then we can put that together. So what we've got, and the two g's will cancel. So we've got v dash squared on sine alpha minus mu cos alpha equals v squared on sine alpha plus mu cos alpha. Now that's looking much more promising because we've got an expression here involving alpha, mu, and the ratio of our velocities, which we know is 2. So what's the most sensible way of doing this? I think probably we want to rearrange that, don't we? So let's put that all in an expression. So if we'll go for v dash over v all squared, and we'll go for that's equal to sine alpha minus mu cos alpha over sine alpha plus mu cos alpha. And now we've got a bit of maths to do. So let's make that nice and big so it's nice and clear. So if I move everything to one side, we've got sine alpha plus mu cos alpha. And then we've got, and that's going to be multiplied by, let's put some brackets in there. Okay, v dash over v all squared, which we know is a half, but let's keep it general for the moment. That's going to be sine alpha minus mu cos alpha. All right, let's put all the mu's on one side. So collect the terms. So mu, what's going to be multiplying by that? Well, we've got cos alpha times v dash over v squared. And we've got a cos alpha from the other one. All right. And then on the other side, we've got sine alpha. And then we're going to take away sine alpha times our ratio. So it's a good job that is definitely less than 1. Otherwise, we've got some negatives, but we can't really gain any more speed than we had with no friction. There we go. And so all we need to do, let's do is change color for that. So therefore, mu is going to be, we just factor out the sines and the coses. All right. So we've got a sine alpha over a cos alpha, which is tan alpha. And then what we've got on the top is we've got a 1 minus v dash over v squared. And on the bottom, we've got a 1 plus v dash over v squared. Okay, and that is the expression we want. Okay, just quite eyeballing what we've got. So remember, I've factored out the sine alpha on one side, the cos alpha on the other side. And we've used our identity that tan alpha is sine alpha over cos alpha. So a little bit of trig. And now let's put our numbers in. So if v dash over v is a half, therefore mu is tan alpha times what I got. I've got 1 minus a quarter. Oops. 1 minus a quarter and 1 plus a quarter. Okay, so that's going to be tan alpha times. So that's going to be 3/4 over 5/4. Right, so I've got 3/5 tan alpha is what I want. And there we go. That is done. So what does that mean? If our coefficient of friction, remember that's just a number, is 3/5 tan alpha, all right, then our little projectile, well, it's not really a projectile, sorry, it's our little body, which is sliding up the slope, will come back down and will lose half its velocity. Okay, so I think there's lots of nice kind of paradigm examples in there. We've taken our time over it. We've used Newton 2, we've done a diagram, we've resolved forces, and then we've been careful about conservation of energy. And we've stayed algebraic. Well, we have to because we're not actually given any numbers here. Do we have any questions I can field?
Yeah, there's a couple of people asking why we just didn't consider the whole movement in one thing, doing something like k before equals k after plus like fr times by 2x.
Okay. Well, I suppose we could sort of do that sort of work. I suppose, yeah, I guess so. Yeah. We could probably simplify that a little bit rather than going up and down, because the total distance we move is 2x. Sure. I suppose in terms of we need to be very careful about, because in terms of working out what the kinetic energy is at the end. I suppose you could think about, because the GPE loss we can ignore then as well. So that might shortcut it. Give it a go, but just be careful with the signs that we're using here. Another way of doing it, of course, is to work out the acceleration and go up and down as well. But you just need to be careful. Remember that the force itself will oppose the motion. So the sign of the force, the friction force, will change. So if you're doing dynamics, you've got to be a bit careful there. All right. So there might be a more efficient way of doing this. I don't have a monopoly about these things. But there we go. I suppose the way I've done it is you can see that the GPE and the GP lot, it's GPE gain and loss. And that's how you might kind of go about it. Okay. I suppose one commentary on this is that if you did it a different way, you may not be able to work out the height that it goes. So that might be something to think about. All right. So because what we've got is two equations essentially for how far up the slope it goes, and then involving that distance as it slides down. So you might get stuck there in terms of how many equations. We've kind of got to get rid of the unknowns here. Anyway, I've not done it the other way. So maybe you can think about that. Any more questions? That's a good one. No, am I still broadcasting?
No more questions, and you are still broadcasting.
Excellent, fantastic. Right, we're going to do a real quickie now, which is I. So now this one always sort of pops out. There's always a sort of a volume and linear expansion coefficient question. It's 3 marks, and actually, I think there's something that might be sort of in the. I know, sort of one. It's not like a major part of most sort of A-level syllabuses. In fact, we don't even need it. The kind of the terms itself in bold kind of tell you how to do it. So this is one of the questions you could get 3 easy marks if you kind of make a sensible guess about what's going on. So let's go and do that one. So firstly, let's just draw a picture, and I'm going to label these things. I'm going to call this thing this volume expansion of oil. And remember, it's a number per degree Celsius. Okay, so if you multiply this number by a temperature rise, you've got some sort of expansion factor of volume. So I'm going to call that K oil, and I'm going to call this K steel. Now, what's interesting here is that we've got a volume and a linear coefficient, right? Okay, so let's just get a sense of what's going on, right? So we've got this cylinder filled with oil. Okay, so here we go. All right, here's our oil drum. This is a steel drum. Okay, and it's at T equals 5 degrees Celsius. So I'm just sort of unpacking what's going on here. All right, so I'm going to draw a picture, and this gives me a little displacement activity to gather all my thoughts together. So this is oil, and there's V oil. So my practice is basically I'm going to draw a diagram, and I'm going to label everything I think is useful. So what happens? Well, on a warm day, temperature rises, all right, to some unknown temperature. So let's just call that by delta T, which is what we want to find. And so what we need to do is that's going to be, so 5 degrees Celsius plus delta T is the thing we want to know. Okay, right. So that's going to be, the drum's going to get a little bit bigger. Okay, so it's going to rise. So the idea is that steel will expand, but so will the oil. Okay, and we're told that this oil leaks a bit. All right, so there we are. There's some oil. Let's have a oil color. There we go. There's oil color. There we are. Oil's traditionally black. Okay, so there we go. We've got some goop coming down here. You won't get any marks for a nice, beautiful diagram. Although I don't know, diagrams you will, but perhaps the beauty of it and the artistry. So I'm not going to get any marks for that. There we go. Here's my oil drum. Okay. But in all seriousness, the diagram, even if it takes only a few seconds, gets you to sort of anchor your thoughts. So there we go. And we've got an oil spill here. Here's my oils, which I spilled. All right. So what have we got? And we're told 2.4% of the oil spills out. So let's give that a symbol. You can use what? I'm going to use eta for this one. So eta over 100, because eta is a percentage, V oil is the spill volume. Okay. All right, and there we go. My temperature now is a balmy 5 degrees plus delta T. Okay, so that's what's happened. So let's do a sort of the oil leakage volume, because why would we want to do that? Well, if you think about it, we need to do some sort of conservation here. So the oil that we spill is going to be the difference in the volumes. Okay, so let's just write that out in words. So the oil leakage volume, what is that? Well, it's going to be the extra oil volume due to thermal expansion, but we're also going to increase the volume of our steel as well. All right, so if the steel were to kind of increase by a little bit, then, you know, if the oil didn't expand, that would sort of like, you know, shift down in the drum. Okay, so we can't just talk about the volume of the oil that's expanded. We need to also take away the volume change of the steel drum, and that's where the extra marks are going to come in, right? And if you think about it, we need to have that because we've got both those numbers, and it'd be a bit silly for us to give both numbers if we didn't need them. So let's just write that down. So we've got the extra oil volume due to thermal expansion. All right, and we're going to take away from that the extra steel volume. Well, it's a steel drum internal volume. Let's just do that, shall we? Right, it's not really the steel so much. I mean, obviously the steel is expanded. It's the internal volume is what we want, and that's kind of important as well because it's a linear coefficient. Oh, right, okay, due to thermal expansion. Okay, I hope that's readable. Okay, so there we go. The oil leakage volume, the eta over 100 times V oil, is how much the volume of oil expands by, and then we need to take away the extra sort of internal volume we've got. So what are those things going to be? Well, let's make an equivalent statement. So we've got eta over 100 times V oil, right? What's going to be our extra oil volume due to thermal expansion? Well, if you look at it, it's a volume expansion coefficient. That's going to be K oil. All right, and it's a volume expansion, right? So it's going to be what fraction of the oil expands over the temperature rise. So if we do K oil times delta T, that's how much we are expanding by. So I guess that's a bit slightly other difficult thing is what does that number actually mean? It's a fractional expansion. Okay, so probably if I was being nice, I might add that term. Maybe we can ask BPhO to do that for future years. But that's what it means, guys. If you're if you're not sure. So K oil times delta T times V oil is what that extra volume is. Okay. So I noticed that it's got to be a kind of factor because we haven't got any other units there. All right. It's not like per unit volume, something like that. Right. And now we need to do the other one. Now here's an interesting idea. So it's a volume, it's a linear expansion coefficient. So we are going to be expanding in 3 dimensions. So we're going to multiply it by 3. Okay, that's the other, I guess, hard point here. So K steel, V oil, delta T. All right. And why is that? Well, because it's the internal volume, all right, which is originally V oil. All right. So let's point that down. Originally V oil. All right. And it's going to expand in 3 directions. Okay. So let's just mention that. So it expands isotropically in 3 dimensions. Okay, so we're kind of done really. So all we need to work out is delta T. So we've got another little bit of factorization. So eta over 100. Let's make it an eta, not an n. All right, so V oil. And we've got K oil, V oil, minus 3K steel oil equals delta T. And of course, my V oil cancels rather nicely because we're not told what it is. So all we need is just the things that we've got. So therefore, what's eta? Eta is, what do we say it is? 2.4%. So we got 2.4 divided by 100. And K oil is 7.0 times the minus 4. Minus 3 times K steel, which is 1.2 to the minus 5. And that's in delta T in degrees Celsius. And I think if you put that into a calculator, you get 36.1 degrees. And don't forget, we want the actual temperature, which is 5 degrees. So we need to add 5 degrees for that. So therefore, temperature on the day is going to be 41.1. It's a shame it's not 42 degrees. There we are. It's close. There we are. So mathematically, quite a simple question, really. But you've got to kind of know what these things mean. So there we go. Now you do. If there's one for next year. Do we have any questions?
Yeah, there's a couple asking why we're multiplying by 3 rather than cubing for the steel coefficient.
Yeah. So, okay. So I guess there's sort of 2 ways of thinking about that. If you didn't know anything about this and you cubed it, that would be a really tiny number. So that would kind of feel wrong. So I think it's just in terms of the definition of this, that each thing is going to be expanding by this factor. All right. So, and of course, if you're going in X, Y, and Z, then you're going to be multiplying your volume by 3 there. I suppose it's a definition, really. Okay. So it would make kind of sense, I suppose. Yeah, because what we're doing is we're not talking it's the internal volume, which is V oil, but it's the steel which is expanding. So if you had the volume coefficient of steel, well, is that going to be the same thing? The steel increased by a certain volume. Is that going to be the same fractional increase in your oil as a result of that? So I think in this question, that's why we were doing the linear coefficient of expansion of steel rather than the volume coefficient. But anyway, yeah, so it's a good question why that shouldn't be a cube. But yes, we know it. Even if you didn't really sort of know, you were kind of guessing around him, making think, does this make sense? We can't cube it because that would be sort of 10 to the minus 15, which would be ridiculously small. There we go. And I think if you didn't have the 3, you probably get 2 out of 3 marks for this one, maybe all of them if you did it, wrote it out really nicely. Okay. Do we have any more questions? How are we doing time? Brilliant. Right. We're now going to move, I think there's another quick one, and then we're going to do an optics question. Right. So Q. There's Q. I'm mindful we haven't done an electrical question yet. No, I might set you in a nice electrical question myself next time. Right. So here we go. Now, this is a very cool question. All right. So I haven't had a question in the chat yet. So does anybody want to tell me what the period of a spring, a small spring oscillating with simple harmonic motion is in terms of the spring constant? And someone put that in the chat. What's that going to be? I think this might be in your formula sheet. I hope it is. So you kind of need this fact for this question. So
Getting lots
okay,
of 2 pi square root m over k, 1
brilliant.
k over m.
Right, it's m over k, so we could do that kind of dimensionally, but yes, and I think if we got time, we could probably derive that as well. But let's use that idea. So if you've got a spring, let's have it. Here's a little spring, all right, and oh, that's interesting. Oh yeah, just got a bit of a delay here. Is that still coming across all right?
Yes.
Yeah, good. Yeah, my mass just disappeared. So here's a mass on a spring, and let's have that mass coming down here. All right, so if you've got some oscillations about equilibrium, right, so I don't know, let's say that's like equilibrium, we've got oscillations about this. All right, so your mass, let's just say that distance, let's go downwards, let's call that downwards is x, for example. So I get a spring and I've attached it to something like a retort stand or something like that, okay? And there's x, right? So maybe I start with a large displacement and it will oscillate like this. A simple harmonic motion means a sinusoidal oscillation. So that's time, okay? And that's the period, t, in this case. All right, so what have we got? So x is going to be, let's call that x naught. All right, so x naught cos, now 2 pi radians, all right, times however many periods we've got, and that will map a sinusoid onto this sort of thing. So 2 pi divided by t over big T. So however many periods we've got is a number of 2 pi radians. So that's what will define that curve. So what's T in this case? Well, that's spring constant K. And just remind us where that comes from, that the stretch of the spring, if we put some forces on this, that's mg. And that's going to be K times the amount of stretch. And now I'm going to write stretch rather than x here because x is going to be the displacement from equilibrium. We'll derive this in a moment. I just want to give you a flavour of what that means. So the K is the stretch force divided by the amount of stretch. That's Hooke's law. So what we find is that the period t, all right, is 2 pi root m on k. All right, that's the period of our mass spring system. Again, I'll derive that in a moment. So there we are. That's the period of a mass spring system. You could just look up on your formula sheet if you were doing this quickly. All right. What are the facts we know? So in this particular case, we've got a car driving along a road with these little bumps. Okay, so we can imagine this is sort of road here. There's a little bump. There's a little bump, and they're separated by distance d. Okay, so here's my car, my high quality drawing of a car. All right, and it's going at velocity v. And the mass, that's going to have, that's what 80 is. So 880 kilograms is my mass. Okay, and we've got it sort of sinks down by 1.8 centimeters. So we're sort of assuming our car has got some springs. So we've got a kind of, this is a resonance problem, all right? So this is what I've kind of stated here, all right? I've got some facts about the period of a mass spring system. How does that link to what we're talking about? And I think this is a resonance problem here, all right? So now, can someone define for me in the chat what resonance means? What you think it means? What have we got, Alex?
We've got driving frequency equals natural frequency.
Yeah. So if we kind of if you sort of get a mass spring in, you pull the mass down, but if you were to sort of shake that whole thing, you know, that sort of retort stand, if you kind of shake that up and down at the same frequency or same period as a natural oscillation, you get bigger and bigger oscillations. Energy gets fed into that system really efficiently. So the time between the bumps, if that's the same period of the oscillation of my suspension system, that's not going to be very comfortable. We're going to get a maximum amplitude of our oscillations, right? If you've ever gone along a road, I once decided to visit the nuclear power station in the east of England near Canterbury. That's Dungeness, a cracking thing to go and visit. All physicists should go and see a nuclear power station, but the road approach from that is awful. And at the speed I was cycling, this actual thing happened to me. There we are. So there we are. If you ever visit Dungeness, you go at a certain speed, obviously cycle rather than drive a car, you will experience this problem as they fix the road. So what's going on? We're going to say that the time between the bumps, is approximately equal to t. All right, and this implies that the oscillation amplitude, it's a driven oscillation, amplitude of the suspension, right, will maximize, right, uncomfortable ride. Okay, right, so there we go. And what we're saying is it sinks by 1.8 centimeters. That's the equilibrium sink, if you like. So that's kind of like x naught. All right, so let's go and work this out. And that means we can kind of think about our spring constant. So let's just do that first. So in equilibrium, so here's our sort of spring. All right, so if we've got our spring in equilibrium, and I suppose the idea is that you've got a kind of compression of the spring and you've got your sort of mass on it. All right, so your mass is acting downwards, mg, and your force here is going to be k times the compression of my spring, which we're told is 1.8 centimeters. So 1.8 times 10 to the minus 2 meters. All right, so therefore, in equilibrium, we can work out the spring constant. So K is going to be, what's the mass? 880. So 880 kilograms times 9.81 newtons per kilogram.
Andy,
hello?
There are 4 passengers.
Oh, is it 4? Yes, indeed. There we go. 4. So my sums aren't quite right here. Thank you very much indeed. That saved my blushes. So what we've got, the mass is not it's not just one person. We've got 4 times 80 plus 800. There we go. Kilograms. Right, let's put that all in. Thank you very much indeed. My students are excellent, aren't they? So it's going to be 4 times 80. Now we have a question here. The mass of the car itself, does that matter? Because if you think about it, this sinks down once the 4 passengers enter. So actually, this isn't right either. Aha! So the 800 kilos is a red herring, right? Because the springs have already sunk. All right. So the extra mass that we add is 4 times 80. Sneaky, isn't it? Right, so there we go. So 4 times 80 kilograms times 9.81 newtons per kilogram, right? Divided by the sink distance, 1.8 times 10 to the minus 2 meters. And that will give you a spring constant of about 1.74 times 10 to the 5 newtons per meter. There we go. Sneaky, eh? All right, so there we are. So yeah, the word is when 4 80 kilogram passengers enter. So now we've got that, and now we can put that into our formula. And well, what's our period? Well, that's going to be our distance over the speed. So in this case, t is approximately, right, distance divided by our speed. All right, so if we can sort of put that all together, what have we got? So therefore, we've got distance divided by speed equals 2 pi square root m on k. Remember, in this particular case, now hang on a minute. So in this case, yes, we do need to get, because that's the period of our mass spring system. All right. To work out the spring constant, it's sinking by 1.8 centimeters. So that's the extra mass we've got. But in terms of the whole system resonating, we need to actually incorporate all of it. Okay. So in this case, the m needs to be, sort of 800 plus 4 times 80 kilograms. All right, because that's the whole thing that's oscillating. But the k here is what we had before. So what we're trying to find the speed, I think. and we're told that the speed bumps are 8 meters apart. So there we go. We're almost done. All right, so that's D. So let's put that together. So therefore, what do we got? We've got, so D over 2 pi times K on M square rooted equals RV. So there we go. There's a nice algebra expression for us to use. Over time, we are good. And therefore, let's put in the numbers. So V is going to be 8 over 2 pi in SI units. K is 1.74. And we're going to divide that by the mass, which is 800. Don't forget the mass of the car, plus 4 times 80. And I make that, that's in meters per second, I make that 59 meters per second, which is a bit faster than I think I can say. Oh, no, maybe not, actually. There we go. Right. So, yeah, a little bit of sneakiness, but it's quite a cool problem, this, I think, because, you know, it doesn't really imagine that this is all about resonance, but it is. So there we go. We've got the period of mass spring system. I will quickly derive that for those of you who have not seen that before. Do we have any other questions about this particular one? Any questions?
No, just I mean, there's people asking about the formula. So, and someone about the D that we've got in here.
Right, so that's the distance between the bumps. Yeah, so basically what we want is the time between the bumps, which is saying is going to equal to the period. That's the kind of key, that's the crux move of this problem. I think if you've stated that, you definitely would get a mark, I imagine. So the time between the bumps is going to be equal to the period of your oscillations of your mass spring system. That's the key point. All right, and time is just going to be the distance divided by the speed. Okay, so let's just quickly derive this. This is a nice derivation. But I suppose there's a little bit of sneakiness for this. So if we hang a mass spring system like this, so this is an aside, everybody, all right, and we've got, let's just say our original length is L. Because I think, and I remember being sort of a bit stumped by this at university myself, is that, okay, this is fine, but what happens when I incorporate gravity? Don't I have other forces? Why does that not appear? So let's just do that. So what we're going to assume, let's just say in equilibrium, we have a stretch of Z. All right, so this is an equilibrium. All right, so what do we got? We've got forces. We've got Kz by Hooke's law. All right, let's assume we've got gravity. So we assume we've got a Hookean spring. All right, so the restoring force is proportional to the extension. In this case, the equilibrium extension is Z. Right, now let's extend it by a little bit more. And then we'd let it go and let the whole thing oscillate. So what we'll do, we'll put the same, that's the equilibrium stretch, Z, and then we're going to stretch it a bit more by X. I'll use the same symbol that I had for my simple harmonic motion up here. All right, so what's going to be our forces now? Let's just have our mass on the end. Let's have that. All right, so mg is the force here, but now our our restoring force is K times our total stretch, which is Z plus X. All right, and this thing is now going to start to accelerate. All right, so if I sort of define an acceleration and a velocity, so X dot, which is our velocity, let's just call that V for the moment. All right, and our acceleration, we know it's going the other way, but let's call that A because X is measured downwards from equilibrium. There's our equilibrium position. All right, and G is acting like this. So if we can write down Newton 2, we've got mass times acceleration is vector sum of force. So in this case, mg minus kx minus kz. So that's our Newton 2 expression. And of course, for an equilibrium, all right, we've got the weight equals kz. So that means all the weight is taken into account by our initial equilibrium extension. And this is kind of what the problem's going on about, right? That the mass of the car produces an equilibrium compression of the springs. And then when the four people get involved, that expresses it a little bit more, okay? So if we rearrange that, what we've got is that A equals minus K over M X, okay? So that is an expression of simple harmonic motion. The acceleration, all right, is minus dependent on the displacement. All right, so if we draw a graph, that's what it would look like. There's the acceleration, there's X. All right, so the gradient is minus k over m. So we might expect that to have sinusoidal or cosinusoidal forms. So we could do some integration here, but we don't have to. All right, but we do need to do some differentiation. So let's assume that our displacement versus time is a cosinusoid. So x naught, and there's our period. All right, so we're going to assume that x goes as x naught cos 2 pi times the number of periods. That's we could do that from experiments, and we could say it looks a bit like this, or we can have a guess. And in fact, when we're solving differential equations, this is a differential equation because a is the rate of change of velocity, the gradient of the velocity time graph, and velocity is the rate of change of our displacement. So in calculus terms, we'd have to integrate that twice. All right, and for solving differential equations, one of the best things you can do is kind of guess, have an educated guess, put it into the equation and see what happens. Right, it may not be the most general solution, but it's certainly going to give you one of them. So we're going to differentiate this. Cos goes to minus sign. This needs to be in radians. So dx by dt, which is v. So the velocity is going to be 2 pi on t. We bring out the factor of time here. We've got a minus sign because cos goes to minus sign. X naught sine 2 pi t on big T. And if we differentiate it again, we find the acceleration. So we've got minus 2 pi on x naught cos 2 pi t on big T. And hopefully you'll notice, all right, that we've got back to what we had before. So if I just highlight the x term here, all right, where is that? Well, it's here. All right, so what we've got, if we assume a cosinusoid, the acceleration is minus 2 pi on the period squared times the displacement itself. And that, if we compare this to what we did from Newton's second law, so I'll just put a little arrow there, right? What we're playing is a game of spot the period. That's what we play for simple harmonic motion. So therefore, 2 pi on the period squared is equal to k over m. And if we flip that upside down and square root, we've got t equals 2 pi root m on k. And every self-respecting A-level student should be able to do that. So if that's new, welcome to the world. But hopefully many of you will have seen that before. But that's a nice, that's not the only derivation of it, but I think that's a nice flow that gives you some insight. And we've not had to do any integrals. Hurrah. Okay, so there we go. Hope that's been fun. We've got a few minutes left. So I think I was going to have a look at T. Is that going to take too long? Let's have a look. Do we have any questions about this before I do?
There's some question not about the derivation, but about the sort of the setup and where the resonance occurs. So sort of what happens if we change the mass of the car slightly or change the distance between the bumps slightly? Do we still get resonance?
Right. So okay. So I think in terms of the original setup, so if we just have a little look, so here's our car going along there. We know we've got a mass spring system. So if it's stationary, the equilibrium is resulting from the total mass, total compression. All right, but it's and we've said in terms of finding out the spring constant, we found out the extra equilibrium sink, if you like, by 1.8 centimeters. Okay, so how have we done it? The extra sink allows us to equate to the extra mass or the extra sort of weight, and that allows us to find K. So that's the purpose of that. So let's just say we've got a spring with spring constant 1.74 times 10 to the 5 newtons per meter. So that's what we've got. That's what our car suspension represents. All right. So what we're doing is we are looking at oscillations of that mass spring system. That's the model of our car suspension. So that's the one that has 2 pi root m on k, and m is the total mass, 4 times 80 plus 800. So we're going to get some resonance if the driving frequency of that. So every time we hit a bump, we kind of get a jolt. All right. So the frequency of the jolts, if that's the same frequency of our natural frequency, we will put energy into the system. Now, we're not really trying to work out what that might be. We don't really know the sort of forces involved, but we know that's going to increase it. And that's going to be the most efficient way of increasing the oscillation amplitude. So that's the kind of idea. So what I'm sort of highlighting now, is this, okay? All right, so there we are. So the time between the bumps is approximately equal to the amplitude, the time of the period. All right. So there we go. Time between bumps equals the periods of the oscillation. That's the principle. All right. And then we can just sort of use our simple models of mass spring systems to work this out. Okay. Time is ticking. So I think I might stop there actually, because I think I'm going to take a bit more time. So if you're really desperate for the optics question, we will begin that next week, which is T. All right, because we're sort of running out of the quick ones. There's a very nice question. It's a bit longer. So I think the hardest question on this paper is U. But I think we will do something on capacitors next time, which is V. And there's a very beautiful question on mechanics, which is L. So next week we'll do TL, and there's the optics, the mechanics problem, and we'll have a look at the capacitor question, which is V. So I'll quickly show you what those are. So if you want to have a go for next time. So let's have a look. So T is all about a prism. All right. So this is about sort of I guess it's not really kind of dispersion of light. This is about sort of for a particular refractive index, but it's how light bends through a prism. What are we going to do? We'll do a capacitor question, which is this one here. Actually, it's not really easy to sort of describe without drawing it really, but this is a sort of variant of a capacitor question. So if you study some capacitors, that might be a good one to do. And if you've not, this might be a nice way of introducing capacitors. And we'll also do a very pretty question, which is, I'm just going to scroll up, bear with me. And this will probably be maybe our last one of this one, which is this one here. This is beautifully simple. There's a lovely book by David Morin. It's a big red book called, what is it called? It's Morin, an Introduction to Classical Mechanics. And beware when people use the word introduction, because some of the questions are really quite hard. But they're all set up like this. So you've got a stick in a kind of smooth hemispherical bowl, and it's touching the rim here. And what we're trying to do is see how all these things relate to each other. All right, so it's balanced. So there we go. So perhaps what you could do when you're having your soup after this, you can get a hemispherical bowl. You can stick a chopstick in it and see if you can get it to balance. And then we'll consider that problem next time. Okay, thank you very much indeed. Hope that was fun. Do we have any outstanding questions before we disappear?
Yeah, someone wants you to go through the integral from the start.
The integral. Well, it's very sneaky. That's not actually something I'm going to derive for you. I'll give you a link. It's but the actual numbers are very pretty indeed. So does anyone to tell you what those or A and B might be? So let's remind ourselves. So 2 sine x over 1 plus x squared. That's the integrand. We're finding out the area under that curve between 0 and infinity is a ratio of 2 numbers that we all know. So A is by circular reasoning. So can you pop in the chat what you think that might be? If we are using circular reasoning, you may groan at this. What do you reckon, Alex?
We're getting pies.
Pi, yes, indeed. So A is pi. Okay, can I think of another sort of I think if you were from Yorkshire, you might say that B is by gum, right? So what might that be? If you have no idea what that means, you might find that this is a decaying piece of humour. So what might be? What might be?
We've got a couple of E's in the chat.
Yes, good. There we go. So pi over E, how beautiful is that? So the most basic irrational numbers. So to do this requires something called complex variable theory. So I think I'm just going to give you a link to this. There are apparently other ways of doing it as well. So I think, am I still broadcasting all right? So if I bring up my website, I'll stick a link in there, maybe. Right enough for Taylor Swift. There we go. Right, let's bring this up. It's going to work. Here we are. So under the maths page of my little website here, so if you go to the calculus page, And the maths of this is really beautiful. It's all about complex numbers. So you click on it, says contour integration of the complex plane. So I think what I'll do is can I put this into, what's the best way of doing this? I should stick this into the chat. And if you click on that little link there, that will take you all the way through it. But it's really, very beautiful indeed. Right, I think if I do that into the chat, there we go. Voila. Can everyone access this? Is the chat for everybody? Does that work, students?
Watch for me. So
excellent. No, we can't see it. Oh dear.
Alex is the host.
All right.
Panelist. So it needs to be to all. There's a drop-down menu.
Oh yeah, got it. Thank you very much, everybody. Right, I'll try that again. There we are. Voila. Hopefully you can read that. So yes. So hooray! Does everyone manage to see that? Thank goodness. So for those of you, that's obviously quite advanced calculus, but there are a lot of many things, including a Christmas catenary on this page. But one of my students was very much enjoying the calculus toolbox summary. So if you're in the lower sixth or the upper sixth and have been given some nasty calculus homework from your teachers, then this might help you out. And there are some notes and other bits and bobs as well. Okay, hope that was fun. Very much like to see you next time. And thank you very much. I'll see you next week.